You all are here today for our Land Data Users Group meeting. This is our second meeting. We got a great agenda ahead. I'm going to do a welcome and a meeting overview. And then we have a tutorial demonstration from Sky Kaplan on reprojecting PACE data and exporting it into a GeoTIFF format. And then our third presentation is from Dr. Emil Charrington. He will be presenting on development of a cloud-based toolkit for PACE OCI land data. So first of all, just a little bit of logistics. In order for you guys to ask questions today, everybody's microphones are muted. So how you ask questions is you go ahead and type them in a question and answer panel, not the chat panel. So to do this, take a look at the bottom right-hand part of your screen, and you'll see there's kind of 3 dots down here at the corner. Click on those and then select Q&A from the menu that pops up. And please send us your questions there. That helps us kind of keep the chat, not lose the questions in the chat. As for today, the knowledge and experience level that we're kind of assuming for our presentations today is that most all of you are familiar with downloading and interpreting satellite data products, and we're hoping that you have watched our first meeting. If you have not, you can always catch up after this meeting. And that meeting gets you up to speed on the PACE mission as well as our land data users group. Also, for the recording here, our information is current as of July 2025. Of course, data versions, access points, resources, and stuff will evolve with time. And there will be an event archive with a recording of this meeting, our slides, our question and answer transcript document, and the Jupyter Notebook. All materials will be posted online in about the next 1 to 2 weeks, depending on how long the web team has or how long it takes them to get it up there. And otherwise, I'm going to go ahead and get started with my talk for today. So I'm going to quickly go over PACE in this group in a nutshell, just give a little very quick overview for those of you that are new, which is quite a few of you. I'm going to do a survey recap from the last meeting, and then do a really brief high-level overview of kind of current capabilities for using PACE data in GIS and GEE environments. All right, so the quick, PACE in a nutshell. PACE stands for Plankton Aerosol Cloud Ocean Ecosystem Observatory. And the science goals of PACE are advancing and extending ocean biological, ecological, and biogeochemical data records, as well as cloud, aerosol, and data records. PACE was launched just last year, February 4th. Our first data release was April 11th of last year. We have 3 instruments aboard the observatory. There's OCI, a hyperspectral scanning radiometer that has coverage from the UV through the visible through the near infrared at 5 nanometer spectral resolution, as well as 7 shortwave infrared bands. PACE also has 2 tiny but mighty polarimeters. One of them is HARP2, which is hyperangular, is its specialty, and then it's multispectral. And then we have SPEX1, which is multi-angular but hyperspectral. For details, again, please see our past meeting. There's a great animation here at the QR code that shows the swath, kind of the footprint of each instrument as they go over Earth and gives you details on each instrument. So as for what is PACE's coverage, so PACE has 1 to 2 day revisit time, global coverage. It's a polar orbiting satellite with a 1300 local equatorial crossover time. And we have 1.2 kilometer spatial resolution at nadir. In practice, it's a little bit coarser than that. Data products are free to everybody, as with all NASA data products. And I want to emphasize the fact that PACE has combined broad hyperspectral coverage, plus its global coverage with a high revisit rate is pretty unmatched by any other sensor. So we're pretty excited about getting this data out there from PACE. The PACE mission provides, we provide 2 kinds of data products. We have both advanced hyperspectral enabled products that are taking advantage of OCI's capabilities. And we also have heritage products for land and ocean and atmospheres. So PACE is really a cross-disciplinary observation platform. And this meeting is focusing on the land data products from the PACE OCI instrument. We'll probably talk about polarimeter products in the future as they become available. What land products are available now from PACE? First, we have the hyperspectral enabled type of products. We have surface reflectance, which has 122 bands of surface reflectance that you can use to do your own algorithms or look for spectral fingerprints. Plus, we have 4 vegetation indexes that are derived from that, from surface reflectance, that are all kind of novel to PACE that we're pretty excited about. Our last meeting goes into depth on all of those. We also have 6 terrestrial indexes that are heritage. Those you'll recognize names like NDVI, EVI, and so on. So that's kind of the top level PACE in a nutshell. Since our last meeting, what data updates have there been? We're still on the same version. We're on version 3 of our data. Our next data update is in the coming months. It's on the horizon. I will send an update to the group by email when it's ready. And you asked and we listened. We have level 3 mapped land data products are now available at 2-kilometer spatial resolution. That's a higher resolution than before. Previously, those products were only available at 4-kilometer resolution. For now, they're only available in the forward stream, which means there's just a few files available. But over the next few months, we will have full mission coverage at 2-kilometer for only the land data products mentioned on the previous page. We also have ahead a novel nitrogen dioxide data product. For those of you that work with nitrogen dioxide data, you'll recognize that 2 kilometers is actually very high spatial resolution for that type of product. That will also be coming from PACE in the next few months. Again, I will let you all know by email. We do have a presentation on this and how to access the preliminary data if you are interested from an event that we had earlier this year. And note that you will get a copy of all of these slides. They have a lot of links in them, and you will have a copy of your own so that you can access all of these links. As for a really quick overview of our group, for those of you that have not been to the previous meeting, how do you actually join our PACE Land Data Users group? You just subscribe to our mailing list. It's pretty light on the email traffic. The instructions are there. You basically send a blank email that says subscribe to that address there. And then we really ask that everybody participates because everyone here helps determine the plug meeting content. And you do that by attending our quarterly meetings, bringing your questions to ask our speakers. And you can also, for the future, email us if you would like to present. Feel free to reach out if you have ideas or would like to present. We also ask that everyone respond to short post-meeting surveys. These surveys are what guide our next meeting. For example, here's some results from our survey from the last meeting. If you guys are curious where everybody is at, we have a lot of university kind of research folks. We have state and federal government and private folks as well, with a little bit of nonprofits. And as for, what I asked, what's everybody's expertise level? We have a lot of folks that, are kind of moderate to expert in their usage of satellite data. But most importantly, the graph that I really wanted to get to is this one. I asked, which platform do you use to work with satellite data the most, or which ones? And by far, we have Python, Jupyter Notebooks, Google Earth Engine, and GIS as ways that people interface with their satellite data. We have a lot of resources for Python and Jupyter Notebooks, but not so much for Google Earth Engine or GIS type of software. So that's what this meeting today is about. I'm running a little bit short on time, so I'm not going to go into too much detail on our requested topics. But as I mentioned, in the survey I asked, what are the topics you want to see for the next meeting? We got lots of answers, and as far as some kind of general ones, we saw a lot. As I mentioned, the GIS and GEE environment questions, there was a lot of those. Lots of questions about if we were going to ingest data, if there's any plans for the GIS environments, and so on. So we're addressing that in today's presentations. And we're also going to talk about how you reproject the level 2 PACE data to level 3 PACE data. That's a tutorial today, also driven by your requests in the survey. Everybody also asked for more applications and pilot study examples. We love those too, but unless, it's your turn to show them. We have, kind of whatever Fred has up his sleeve is the kind of presentations that we have. Otherwise, we'd love to hear from you all on your pilot studies, your applications. It'd be fantastic if you could present to the group on what you're doing with PACE data or thinking about doing with PACE data. We got a fair amount of ocean air quality topic type of questions, but I want to emphasize that this group focuses on terrestrial data products. I know PACE does it all, land, sea, and air, but here we're mostly talking about the terrestrial data products. There is going to be overlap. Some of these data products, like the nitrogen dioxide one, could be used across the different disciplines. And also the data access methods that we're going to talk about really apply to any PACE OCI data products as well. I won't go over all the kind of less frequent assortment of related topics that we also saw, but I will say we have events ahead and Jupyter Notebooks and a few other things ahead that should address a lot of the other questions you guys asked in the survey. So again, I want to emphasize, please make sure you fill out our survey. I'll give you the link at the end. It helps us guide each meeting. So the last couple slides I have here, I'm doing a high-level overview of so what is the current capability if you have PACE data and you work in a GIS environment? Right now, your best bet is to download the data from NASA Earth Data, which is the typical way that everybody does. Those are netcdf files. You can convert those to GeoTIFF format and import them into your GIS software. For right now, that's kind of the suggested way to go. If there's a lot of software options out there to do the conversion to GeoTIFF from netcdf. Today's tutorial provides one option using Jupyter Code. We also have CDAS, which is free from NASA, SNAP, which is free from ESA, that's the European Space Agency. And of course, this is not at all an exhaustive list. If you have a favorite GeoTIFF converter, feel free to put it in the chat. And what about the future for if you're using GIS, what's ahead? Well, we're really excited to say that we have 10 level 3 products for land, ocean, and atmosphere that are going to be available by the end of this year from Esri's Living Atlas. So if you're an ArcGIS user, or actually QGIS users can also access the Living Atlas, there will be PACE data there by the end of the year. It will also be available on the NASA Earth Data GIS portal as well. It'll be the same 10 products will be available in both of those places. PACE data is also available through NASA Worldview, which is primarily a visualizer, and we have 3 PACE products there at this time. By the end of the year, we anticipate having terrestrial products added. Right now, it's 3 water products, TrueColor. So again, by the end of the year, we'll have more there. And I mentioned Worldview because not only is it a powerful and easy to use visualizer that exports images, animations, and can also export in GeoTIFF format, it also interfaces with ArcGIS and QGIS using a global imagery browsing service. That would be a whole other presentation to go over, but you can check out that link there if you're curious about what that exactly means. And finally, with Google Earth Engine, we get this question all the time. Is PACE data going to be ingested into Google Earth Engine's catalog? The answer is no, there are not plans at this time to do that, but we have a couple of suggestions, suggested alternatives or actions you can take instead. You can download the data from NASA Earth Data, just like I said on the last slide, convert it to GeoTIFF and pull it into your GEE user account. And as a shortcut, today's presentation from Emil at the 3rd presentation is going to be a really great example of this. And he's going to provide his code repository and his data for you all to use, which would be a shortcut if you would like to use the tools he has. You can also request PACE data ingestion. There's of course no guarantee that Google will decide to ingest the data, but I have instructions here and a link on where you can go to suggest a data set from their catalog, basically from the front page of their website. And you can kind of search through, look for other PACE requests and add your +1 if you see one you agree with. You can put +1, it's like in the upper right-hand corner of the window. And you can also add a comment. And you can also create your own feature request. And if you have a completely different set of data that you would like to request for PACE. And just be sure to be detailed when you fill those requests out and reach out if you have questions. So finally, This is the link to our survey. We would really like you to fill out the survey today after this meeting. This will help guide the next meeting. Most of you are subscribed, but if you're not, don't forget to subscribe. And please email us if you want to consider presenting at the next meeting. I went a minute over, so I'm going to skip questions. If you can put them in the chat, I will work on answering them during other presentations. And I want to go ahead and get to Sky. Get to Sky's presentation. So one second while I switch screens here. So next up, we're going to hear from Sky Kaplan. She's a scientific analyst on our PACE team. She is, you can go ahead and take the share screen. Let me know if you have any issues, Sky. She is a scientific analyst on our PACE team. She has a diverse background with a bachelor's degree in geology and astronomy and a master's in remote sensing and biological science. She's currently the land lead for the PACE mission. So she's the one working behind the scenes here at NASA Goddard to make these great products you all are using a reality. So she's going to present a tutorial from a Jupyter notebook on reprojecting PACE OCI data. Take it away, Sky.
You guys can hear me, right?
Yes.
I don't know if you can see me because I think I did this in the wrong order, but the important thing is that you can see the Jupyter notebook.
Yes,
Okay,
definitely see
cool.
that.
Great. All right, so thank you, Morgane, for the introduction, and thanks all of you for logging on today. Like Morgane said, I'm going to give you all a quick overview of how you can reproject level 2 PACE data to your favorite projection, and then how you can export that projected data as a GeoTIFF if you prefer to work with that file type rather than NetCDF. All of this today will be in Jupyter Notebook form, so this demo will be most useful for those of you with some Python and some NetCDF experience. I know that's likely not all of you, so apologies if this goes over anybody's head, and hopefully you can hold on until Emil's presentation after this. So this is going to be kind of like a pseudo live demo in that I've already run all the cells and this notebook is active, but for time and because live demos always seem to have issues, I'm just going to scroll through and talk you through all the cells. Also, I should say that this tutorial is in its final draft stage, and so it's still under development, which means two things. One, it isn't on PACE's Help Hub yet, but should be soon. Right now, you can find it on my personal GitHub if you want to go over it later or in time with me right now. And I can put that link in the chat afterward because I don't think I can see the chat right now. The second is that it's technically still a draft, right? So I'd welcome any feedback all of you have if you're working through this and you see something that you think I should change or you think I should add, please email me or talk to me afterward in some form. And I'm happy to answer any questions that come up as well. All right, so let's jump right in. The first cell, this setup cell here, is setting up the tutorial where you'll import all of the packages you need to reproject and reformat PACE data. The most important thing here is to make sure your Python environment is set up to the most updated version of all of these packages, as the utilities that allow us to work with level 2 data is fairly new. This especially goes for the Rasterio, X-Array, and Rio X-Array packages, as these are the ones that allow us to do any of this reprojection in the first place. We can now grab the data. Yes.
Sorry to interrupt. Is there any way to make the print a little bit bigger?
Let me see if I can. How's that?
Yeah. Oh, yeah. That's much better. Great.
Beautiful. Sorry about that. I should have known my eyes are also terrible.
No worries. Thank you.
Yeah, of course. All right. So that's the import step. And now we can go and grab the data that we're going to use to convert our files. So we'll use the Earth Access package, which basically allows us to access any of the data available on Earth Data Search through Python. The way I have this set up is to download the data to your local system, but you can modify it to stream the data if you're working in the cloud. We have a whole tutorial on that on PACE's Help Hub as well. If you're not familiar with this process, it's super useful. Instead of having to go back to different tabs and download data, you can just do it directly here. Like all of you heard, if you were in the last land data users group meeting, there are two types of PACE land data right now. So we have the vegetation indices and those surface reflectances. And the structure of those files is slightly different in that they have different number of dimensions. So the indices are 2-dimensional since they're just a single number for each lat long combination. And the surface reflectances are 3-dimensional since you have 122 wavelengths for each of those lat longs. These dimensional differences necessitate slightly different processes for projection and formatting. So we're going to download a granule from both, which is what we're doing again here, and go through the process for each one. So I've run these cells. Don't worry about the coming soon bit. That's supposed to be a preview of the granule once Earth data has the functionality implemented. And don't worry about these widget errors either. They're supposed to be process bars for the download. I have no idea why they chose today not to work, but rest assured, the data is downloaded. All of these cells are working properly. So we can start with the simpler 2D variables, so those vegetation indices, and we can use X-Array's data tree method to open each file's whole data tree, so that's each group with all of the information in it. This cell here demonstrates the dimensional differences as well, so you can see that the surface reflectance has number of lines, or the Y dimension, pixels per line, or the X dimension and wavelength, which is like a Z dimension, whereas the vegetation indices only have number of lines and pixels per line. And in the chlorophyll index plot here, we can see that this level 2 data is not on any sort of regular spatial grid, and instead is still in the instrument swath, plotting each value for its location in the array, those X and Y dimensions, not its location on Earth, which would be the lat lons. And we'll change that by the end of this tutorial. So the basic steps we have are to mask for any quality issues or obscured pixels, to set the coordinates to the latitudes and longitudes in those arrays, to assign the spatial dimensions as columns, X, or pixels per line, and rows, Y, number of lines, and assign a coordinate reference system. And then finally, we'll use RealXArray to reproject our data set to a destination data set. And that's what all of this is saying here. And I will say there's a lot more information in this text than I'm saying out loud for time's sake. If you're going through this, please read through all of it. Hopefully some explanations will be much more clear. So to do the masking, we will use the L2 flags variable that you can see if you print out the data set with X-Array. So that's that last one at the bottom there. That's where all the quality information is stored in level 2 PACE data. And there are a bunch of different flags available to us. I have the link in the tutorial as well. But for simplicity here, I'm only going to be masking out clouds, noting that the vegetation indices come pre-masked for water as well, which you can see in the plot up here with all that white space. So if we scroll down a little bit, I can show you that we're using the CF X-Array package to kind of handle all of these flags. So the first line here in this cell is saying if CF X-Array, which is a utility that allows us to mask, recognizes L2 flags as a flag variable, we can then create a cloud mask by keeping every pixel that is not identified with the CLD ICE cloud ice flag, and then apply that flag to our source vegetation index data set. And when you plot that, you can see that there are a lot more pixels masked than in the first plot. And that's because every one of those pixels was identified as a cloud pixel, which you don't need if you're working with vegetation index data. I know there are probably some cloud people here. Sorry to mask all your fun data out, but for these vegetation indices, we don't need them. So we are left with only our clear sky pixels. And that next step in our reprojection process is to assign the latitude and longitude arrays as coordinates for the data, basically telling the data set that the geographic coordinates should be associated with each pixel rather than treated as an individual variable. This information is located in the navigation data group, which is basically just what I'm doing here, assigning each coordinate longitude, grab it from the navigation data longitude group, same thing for latitude. And we also need to set some spatial dimensions, which are those swath dimensions representing the columns and rows of our data, so that we can set the source coordinate reference system. This can all be done in one step. Basically, your spatial dimensions are your X and Y, and then your CRS is EPSG 4326 because our geolocation is based on WGS 84, and that's why we use this one as our source CRS. If you then print out the data set again, you can see several changes from the previous printout, namely that we have longitude, latitude, and spatial reference coordinates now. So that means that this data set is geolocated in X-Array. So in this next cell, if I scroll all the way down, this new font size makes scrolling a little longer. Sorry about that. We'll create the actual reprojected data set with RealXArray's reproject function. So that's what we're using here. And the whole reason we're able to do this reprojection is thanks to their implementation of the source geolocation array argument, which is this very important part there. And that will take our 2D latitude and longitude coordinate arrays and use them to transform the data into whichever CRS you choose. Here we're just transforming into WGS84 again for simplicity's sake. But if you have a preferred projection, you can choose whichever one and assign it there. And this step might take a second or two, depending on how big your data set is. But once it's done, we can plot the data one more time and see that each pixel is correctly projected and geolocated and can even be plotted against a base map, which is what you're seeing here. So you've got the latitudes on the y-axis and longitudes on the x-axis, actual projected array, which is what we wanted to end up with. So before we do any sort of exporting, I will go through the 3D variables for surface reflectance. Typically, we could just use the 2D method that we went over to project these 3D data, and it would work fine. However, like Morgan said, one of the goals for this tutorial is to make the data usable in GIS softwares like QGIS, which require dimensions to be ordered Z, Y, X, where Y and X are positional dimensions like latitude and longitude, and Z is a third dimension like wavelength. As I said before, and as this next cell demonstrates, the dimensions for our surface reflectance variable rho s are y, x, z. So it's kind of flipped from what QGIS expects. And the easy fix for that is to just, if I scroll down, do a simple transpose so that you get the z dimension in front of y and x. And I should also note that GIS programs like ArcGIS sometimes seem able to decode our dimension order without this transpose step. But from my experience using QGIS, that's the software that I work in most of the time. If you load them in just kind of raw, you won't get that. You won't get the actual data. You'll just get some weird looking nonsense just because the dimension order is different. So I figured this would be a useful step for all of you. Another difference from the above 2D variables that you might notice here is that we set the source data set to just the rho s variable. That's the line above the transpose. And if you recall, the L2 flags variable is two-dimensional, while rho s is 3D. And the packages that we're using to reproject and format these data can't handle the different dimensional architecture. So we just have to exclude that 2D variable. And all that means is that if you want your surface reflectances masked for anything, you should do that before you go on to reproject. And now that we have our data transposed, the steps from the 2D variable reprojection can be followed exactly. So that's what I'm doing here. This is all just, again, explanation. Probably, written down is a lot easier to understand what I mean than when I'm saying it out loud. But yes, so this is the same process as we had for our 2D variables, setting the spatial dimensions, setting the CRS, and then reprojecting with that source geolocation array. And then if we can plot the data, we can also see that the surface reflectances are happily and properly georeferenced and reprojected. And now if you're happy working in Python, you can stop there. For those of you who prefer GeoTIFFs, the final step is to export your dataset with the RioXArrays to raster method, taking care to adjust these profiles as needed. So these profiles are basically telling the program what you want in your dataset when you export it. For example, if you prefer a different no data value, you can substitute your value in for mine, where I put np.nan. You can put -999, whatever you prefer in your data. And this little cell here will export both the surface reflectances and the VIs to a GeoTIFF. And then finally, the next cell is just a function I wrote to do all these steps for you in one. If you've gone through the tutorial and feel like you just want a quicker way and you understand everything, you can feel free to grab it and edit it for your own use. This just basically takes a file path that you provide and kind of checks if it's a surface reflectance file or if it's a land VI file. I should note also that I don't mask for any clouds or anything if it's a surface reflectance file, but if it's a land VI file, I'll mask for clouds, and water is already masked. So this is a huge function you can edit to your desire, but it will do all of those steps above for you. And finally, just to say a bit about our level 3 data, reprojection for this data type is much, much simpler because L3 paste data is already mapped to the Platte-Carré projection. So if you want to work with it as a GeoTIFF, all you need to do is assign the CRS and export it to TIFF with the terraster method, remembering to transpose the 3D data if you want to work with it in QGIS. But yeah, that's it. Hopefully this was helpful for those of you who are wondering how to use L2 data in your workflows. As I said, I'm happy to answer questions, and I know this was super fast, so yeah, I'm around if needed. Thanks.
Thank you. Thank you so much, Sky. That was that's really a great resource. We've had several people ask, they want to make sure they get a copy of it, and we will make sure you all get a copy of it. We will try emailing it. I say try because I haven't tried yet emailing with attachments to the list, to the email list. But regardless, there will be an event archive that gets put online. I put the link in the chat where all materials from this meeting will be posted, including that notebook. And actually, Sky, isn't it correct that this will, once it's finalized, go on to Help Hub? I think you said that in the beginning.
Yes, so this will go on Help Hub. Right now, it's on my personal GitHub, which I've just posted the link to in the chat.
Oh,
So you should
excellent.
be able to see that version of it. But
Okay.
yeah, eventually, once it's finalized, it'll be up on the Help Hub.
Yeah, and when we talk about Help Hub, if sorry if I'm duplicating what Sky said, but it's where we're pooling a lot of resources like Jupyter Notebooks, as well as training videos and whatnot to help people work with PACE data. So that's what it means when we say Help Hub. I'm not, let's see, I think I'm checking out the questions, the other questions. I think they're getting addressed. We had one person that asked for tutorial on how to find satellite data matchups if we have in situ data. And we do have one of those on, we do have such a notebook. I will put it in the chat here right after during the next presentation. It's from our Hack Week. So every year we have what's called a PACE Hack Week, which people can apply to, where they spend a week here coding with us. And the result is a lot of Jupyter Notebooks, a lot of learning, and everything is archived online. And we will send you some notebooks that address that exact question of matching up in situ data with satellite data using Python. I think that's it for the questions. If I skipped any, I'll go back and answer them by text. And next up, let's hear our third and final presentation of the day. We have Dr. Emil Charrington here. He is a principal research scientist at the University of Alabama in Huntsville's Earth System Science Center. He supports the Severe Science Coordination Office at the NASA Marshall Space Flight Center as Severe's Ecosystem and Carbon Management thematic lead. He and his University of Alabama at Huntsville colleague Kelsey Herndon have a PACE Early Adopters project focusing on ecosystem mapping in the Mesoamerican Biological Corridor. Emil is also a Google developer expert for Google Earth Engine, and his presentation will highlight the nexuses between PACE and Earth Engine. So Emil, take it away.
Sure. Thank you so much, Morgane, and awesome presentation also by Sky, and also thank you, Fred. Let me share my screen. One moment. There we go. Let's see. Share the whole window. Okay. All righty. I hope that everybody is able to hear me well, and I also hope that you're able to see my screen.
We can.
Awesome. I'll turn off my video. So I guess first off, just again, thank you so much, Morgane, for giving me this opportunity. I just wanted to kind of build off of what Sky has been showing and what we also saw in the previous plug meeting. So I guess without further ado, just to kind of for the next 15 or so minutes, what I'll be talking about, a little bit of context, some kind of why we're doing what we're doing, what this toolkit that we've developed features, and if we have some time, and that's a big if, small demo, and of course then turning it back over to Morgane for a question and answer. So just a little bit of context. It's, I think a lot of people who have joined this call are familiar that there are a number of hyperspectral missions out there, satellites and sensors, in terms of current NASA capabilities. Some of the folks here might have used Hyperion data, which took its first imagery around May of 2001 and its last imagery in 2017. Currently, there's also a sensor called EMIT on the ISS. I believe that a few people, some of the attendees, might be linked to the EMIT science team, and that's capturing, I guess, similar to Hyperion. It's, well, in the case of EMIT, it's capturing 60-meter data. That data, however, is on demand, and not to beat a dead horse, as Morgane just mentioned, in terms of PACE, one of the, I guess, at least what I find really cool about PACE is compared to some of these other missions, it's capturing imagery all the time. And so it's capturing practically everywhere on Earth, daily. The spatial resolution is coarser than some of the other ones. But again, if you look at, just what I have here, the wavelengths that Hyperion and Emit are capturing, PACE is, getting similar parts of the spectrum. So from visible through to shortwave infrared. And as Morgan said before, slides will be shared afterwards. I just also wanted to hark back to the previous plug meeting where Morgan, walked us through, Morgan and Fred and Sky walked us through the different things that are out there. And just in case people have forgotten, there are a number of different land products that are being, pulled off of PACE. And I guess, as Morgan has herself said before, one of the things that blows people's minds is that PACE ostensibly is an ocean observing mission, and yet it's producing all this great land data. And so just looking at the participant list, I know that, some people work in conservation, other people working on ag. I see questions in the chat about agricultural monitoring, et cetera. Just to say that, PACE's data is relevant to so many different parts of terrestrial monitoring. That all said, just building off of what Sky presented just before, and also as Morgan had mentioned, if you want to see PACE data, one of the easiest ways, or at least I know I use for filtering, is looking at NASA Eostis Worldview. Every day it's updated with the PACE data that's there. However, if you want to actually, pull down and touch and feel the data, then, you're likely using either NASA Earth Data Search, or you're using the level 3 and level 4 browser from the OBDAC for pulling that PACE data. But one of the things that, in the context of this early adopters project that myself and Kelsey Herndon are implementing, one of the things that we found is the data is really heavy. And so if you're looking at, say, like a global mosaic at, say, 0.1 degree spatial resolution, which is something around 11 kilometers by 11 kilometers, then that single file that you're going to be using is 1 gigabyte. And the trick is that many of us on here will likely be using more than one specific date. And of course, then if you scale that up to the 4-kilometer data, then you're talking about a 7 gigabyte file. And the new 2-kilometer spatial resolution data that Morgan mentioned, a single file is over 30 gigabytes large. And I don't know about you, but I'm sure that might also be the case for some of the people online. That's just a lot of data to have to use, to deal with on your desktop, and it makes it kind of unwieldy. And so I guess part of that then came up, out of that came the idea of, well, what if we, put this data, where the compute is, i.e. on the cloud, and specifically, what if we put the data in Google Earth Engine? And so the overall idea is for, kind of why a toolkit is to support application of PACE OCI land data. And again, the idea of application. So as Morgan mentioned before, where her and the broader PACE team really do want to hear from the community about the different things that you're either doing with PACE data or interested in doing with PACE data. But the idea is, hey, what if we put a bunch of this data out there, on the cloud and, platform like Earth Engine that we know a lot of people are already using. If we put it there, we supposed that we could then support people being able to do stuff with it. And again, as I mentioned before, the PACE data are huge. It's big data. And Google Earth Engine, or GEE, that, its thing is working with big data. And the other reason too for having it in Earth Engine is there's other types of data that's already loaded into Earth Engine, whether you're working with Sentinel data, Landsat data, JEDI, LiDAR data, MODIS, other hyperspectral data like Emit and Hyperion, it's already there. And so by loading the PACE data into Earth Engine, then we could put that all together. And also the other thing to mention about putting together this toolkit is we wanted not just to give people access to the data, because we realized that having the data itself isn't enough, but give users a head start, and so would allow people to have tools that could allow you to interact with that data. So without further ado, kind of start to show you some of what that has. So far, since the first month's worth of PACE data was March of 2024, we just finished. Obviously, yesterday was the last day of June. We're able then to have something like 16 months worth of PACE data. Some of that data, as has been highlighted before, comes in daily cadence, other products on an 8-day cadence, other products on a monthly cadence. And so just, again, and I will share the link in the chat in just a moment. There you go, for people to start, just messing around with it. But the idea being that, some of these products we've started loading into Earth Engine because we want people to start exploring that. And so this is seen on the screen there, just an example of, what do all of the different global mosaics look like, however, at, that 0.1 degree spatial resolution. In terms of how this all, how we did it, just kind of similar to what Sky was showing, we realized that we could focus on, again, the surface reflectance products, but also the vegetation indices that are out there or available to you. And the idea being, and I'll just quickly kind of walk you through this, if you grab the data from NASA Earth Data Search or from the OBDAC, you're going to get it in a NetCDF format that obviously you're going to say download to your desktop. And then you can use different tools, as Sky and Morgan were talking about, to then convert that to GeoTIFFs, because again, we assume that a lot of the people work with GIS systems. And so you can use Snap, you can use CDAS, and then export that data to GeoTIFF. If you want to get that into Earth Engine, however, you gotta now upload it into Earth Engine. In terms of some of the additional steps that we've been doing, removing no data values, and so a lot of that data is coded with minus 32767 as no data. And for multiple reasons, when you're using Earth Engine, it's good to not have no data in there, so that it's not interacting or skewing your statistics that you might be calculating. And then also the data that you've gotten from in NetCDF format is in a floating format, and then I've been converting that to 16-bit instead of float. And then for the VI data, extracting them apart and then recompositing them for the surface reflectance data, then just taking that data itself as well as with the VI data, and kind of when that data imports, looking at it just to make sure that it is what it should be, and then generating what in Earth Engine are called image collections, or say, stacks of multiple types of imagery. And then all the different data that I've been loading, I've been then also making that publicly accessible. And so that's how you get the OCI data in Earth Engine. What does the toolkit look like? And I'll try to run through this pretty quickly. What does it have? Essentially, sets of functions for discovering data, visualizing data, doing some limited time series analysis, some gap filling of your data, because some of your time series might have some gaps, and some basic tools for image classification, as you can kind of see there. And again, if you've clicked on the link that was shared, you should be able to then see a repo that has a name pace_OCI and has these different folders with files on them. So for instance, in terms of data discovery, one of the first scripts, you can pick a point, pick a set of coordinates, and see not just what pace, surface reflectance, and vegetation index data are out there, but also data from emit and archive data from Hyperion. In this case, I'm looking at Huntsville, Alabama, where I'm based, and I see that there aren't that many scenes from Hyperion, but I see there are 5 scenes from emit and just a ton of monthly data and 8-day data from PACE. Viewing the data, the screenshot I shared before, scripts there just for you want to look at that data and see what it looks like. Use the eye tool in Google Earth Engine to click on pixels and see what the values look like. You can do that. You can also look at spectral signatures. And so something that's been highlighted in the previous plug meeting, particularly by Fred, is if we were to say take a point in time and a place and say looked at what MODIS would look like for that area, you would get a spectral signature that looks something like this. Here I'm using 6 of the bands from visible through near infrared through SWIR. I know MODIS for surface reflectance has 7 bands, but I'm just picking 6 bands here. And then now if you take that same spot and pull up the OCI surface reflectance data, this is a site in Belize. Look at how really neat. That spectral signature comes out. And again, in some of the other presentations, Fred and others have kind of walked us through, different pigments, et cetera, that can be pulled out using this type of data. Time series are now, and by the way, so this one here, we're actually looking at multiple months of spectral signatures. And then, however, we can also, there's another script for looking at, say, a given point in time, how the different vegetation indices behave. And here are the 10 different land vegetation indices provided by PACE on a monthly time scale. And so one of the interesting things we see is that because the different vegetation indices represent different things, they don't, say, behave in the same way or peak at the same times. And then lastly, the other thing that we have some sample scripts there for are simple classifications using unsupervised learning. And as time goes by, I'll be adding to that. And again, just to say, the toolkit, the scripts are out there. I hope that folks take advantage of that. And then just in the next few minutes, I just wanted to quickly also mention that when you do load the toolkit, it does pull on some 3 dependency packages. One which loads different spatial functions, including the original equations for estimating the land vegetation indices, as well as additional VI equations, for instance, normalized burn ratio, what some sample band combinations that you might want to use are, and also the wavelengths for version 3 of the surface reflectance data. And then there's a data loader, which is actually the different data sets I've already loaded into Earth Engine, the specific references to those data sets if you're interested in just pulling out specific ones. And then some sample site locations across Mesoamerica, where our early adopters project is focused on, and also the US. And also just giving a shout out to some of my Central American colleagues like Diego, Delwin, and Jamani, who are here on this webinar. So there's sample data that you might also be interested in. And I guess for the next minute, just, the data loader package. Well, I guess, as mentioned before, there's global data over the continental US, Mesoamerica, some scenes which are at the 1.2 kilometer original resolution, and globally the different VI data that are out there. Also to mention that as the VI data become available, I've been trying to keep those updated, as well as pulling in, again, some select scenes and the idea of eventually pulling in the 2 kilometer data that Morgan mentioned. I think I have just about maybe 4 more minutes, so I'm just gonna put a timer on here, and I'll just hit escape. And for the little time that's left, I think you can still see my screen. And I think that I've zoomed in enough that you can kind of see the names of the different scripts that are there. Again, you have the link in the chat. As mentioned before, there's a data loader script here that has references to the different files that have been loaded, as well as some additional scripts in there for how to create image collections from those. As mentioned, the spatial bandwidths, not just for PACE, but also for emit, also for Hyperion, etc. Sample script, as mentioned before, for being able to see, for a given point. And this is where you as a user, you can put in your own select points. I have other examples there, for instance, from over California, where there was this, the park fire in Paints Creek last year, or around Paints Creek. There's a script there for doing that. Another one, just a reference script in there for discovering and looking at, for instance, Hyperion data archived that are there. And then the other things that I've mentioned before for, say, viewing monthly data over the continental US, viewing data over Central America, noting that, again, some of my Central American colleagues are on this call. That's 4 kilometer data. There's also 1 kilometer, some sample scenes there. And then based off of that, being able to pull out specific spectral signatures for different types of land cover and vegetation that are specific to Belize, like savannas. I think there's another script there with locations of mangrove sites, etc., etc. And then since Diego from the Universidad del Valle in Guatemala is here, sample script also for being able to pull emit data and kind of see what's there. And then, this park fire that was mentioned, I know that Ronan Lucy from NASA Disasters Program is here. Just some examples here of, okay, for instance, for the park fire, what did the spectral signature look like? And the burnt scar we're looking at here is from MODIS. We can turn that off and kind of see what the data looked like in August, but then kind of see what the spectral signatures looked like before the fire and after the fire. And then just starting to wrap up other examples that's mentioned before for looking at those vegetation indices, stuff that Fred has presented before. But for instance, an example from here in the Huntsville area, this is a park called Montesano State Park. This is what one of them 4-kilometer pixels looks like. And so the time series we're looking at is for that specific 4-kilometer pixel. And then lastly, as mentioned before, sample scripts for doing unsupervised classifications using this data. And again, the overall hope is that people will just kind of go through this, and if there are scripts that you find interesting, make use of them, make your own scripts, etc. And then let me just, I think, final slide, just like to acknowledge the support that I've received through this early adopters project from Morgaine, Skyfred, and the NASA Marshall Space Flight Center side, different colleagues who've provided support, and of course, support from Google for storage for these data sets, etc. I guess the big question for you is what you plan to do with the data now that, at least through Earth Engine, you have, you're easily able to access that stuff. And then I guess I'll turn it over to Morgaine for the rest of the call, and just say thank you to everybody. And of course, if you're, I'll also be posting some of this stuff on social media. If you're, on Twitter or LinkedIn, please feel free to give me a follow, and I'll stop sharing.
That was fantastic. Thank you very much, Emil, for that. We do have some questions rolling in. First of all, we have one of the folks on our team wanted to make sure that we make a distinction between the fact that Paste data is in a commercial cloud in the Amazon Web Services cloud via Earth Data, and not just the GEE cloud. Did you want to say anything extra about that, Emil, or?
Yeah. So I guess also from our side, one of the things that we always talk about is that we're data agnostic and platform agnostic. And so as Dr. McKibben just pointed out, you can get Paste data in multiple locations. Earth Engine does have a cost if you're using it for operational purposes or commercial purposes. And so this isn't a, it's not saying, hey, definitely use Earth Engine. However, it's, I guess, one of the avenues of using that data. Back to you, Morgan.
All right, excellent. Moving to another question. This one's pretty specific. It says, what is the difference between harmonic and MT_blend data gap filling?
Yeah, that's a good question, and very somebody's got eagle eyes. There might not be enough time to get into this, but one way of doing gap filling is using harmonic functions to kind of estimate based on essentially how the data have behaved over time, fill in where data might be missing, and then so that's the one that says harmonics. There are people who've done gap filling using harmonics before, multiple published papers on that, and so there's sample code for doing that that's based off of some Modis harmonics work that's there. And then the other one that says monthly blend is essentially, instead of doing it based on harmonics, just stretching out these windows of time to say, all right, if, for instance, there was data missing, say in May, if we average out, with a month forward and a month backward, could we fill it in and, kind of take that progressively? And so that's what's there. But I guess the question also highlights that I probably need to do a little better in terms of documenting what the different scripts are doing. But it's a work in process. Thank you for the question.
All right. Excellent. Moving to the next question. Someone asked, I think that this someone is asking if you have considered integrating your ingested paste data set into the GEE community catalog at geecommunitycatalog.org. It would be great to see it there as well.
Yeah. So thank you for that question too. I just had a call with Sam Roy, who runs the community catalog. I just spoke to him last week, and yes, that is one idea. Is to move it forward through the community catalog. I guess as I have news, we'll share. But yeah, thank you for the suggestion. And just to say, yeah, Sam does a really awesome job of curating the catalog with, I guess, non-standard data sets or data sets which aren't in the public catalog.
Excellent. We have another question on this one. This one actually might be going back to Sky's presentation. But I'll go ahead and read it anyhow. Sky, you may want to chime in on answering this one. Either of you can. Someone asked, I work in agriculture monitoring and require highly accurate geolocation accuracy for time series PACE level 2 surface reflectance products. However, I noticed that even after reprojection, there's a slight variation in geolocation accuracy. Are there any suggestions on how to obtain a highly accurate time series geotiff image? And yeah, I have a little bit of insight on it, but I wanted to give from someone sent me in a text in a chat, but I want to know, do you want to answer that, Sky? Did you guys face this issue when developing the notebook?
I haven't faced that quite. I mean, maybe my tolerance for highly accurate is different. My one comment there would be uh, the thing that you could do is, I guess, reproject or take the reprojections and put them on a standard grid like our level 3 mapped data, and that you can do with OCSSW. I think we also have a tutorial on that on the Help Hub, but that would just properly align the data for the time series so you can stack them in that way. That I don't know, Morgan, what your little text there said, but
Yeah, I just had, one of the folks who helps, James, he chimed in that, maybe it's the best we can do with the 1.2 kilometer resolution. Um, he thinks that the accuracy of OCI is it's 100 meters at nadir and up to 500 meters at the edges of the swath. So that's maybe perhaps some important numbers for you on the geolocation accuracy of the instrument itself. So hopefully that addresses that question. I don't know if you have anything to add, Ian, feel free to in the chat on that topic. Let's see. We also have, are there other, it looks like with the GEE, back to the GEE questions, we have, someone's asking if you could share your LinkedIn again. And someone had some trouble opening the bit.ly link, but some others were able to do it. I don't know if you have any advice on that.
Yeah, just to say really quickly, I thought that the issue with the person who posted there in the chat might be if their Earth Engine project is not set up. But if that's not the issue, I'll also post my email in the chat. And so if said person wants to reach out, I'd be happy to look into that. And even if it's an Earth Engine project issue, I can probably support that as well. Over. Back to you, Morgan.
All right. Thank you. I'm going to check in the Q&A box. I think the next couple of questions will be about kind of general PACE question or L2 data gridding questions for the second presentation. One person asked if there's a standard way for L2 data gridding, and Sky answered that the OCSSW method she mentioned would be the answer to that. You want to look at the L2 bin and L3 map gen sections. She put a link in the chat, or actually it's in the question and answer panel, to where she's referring to for you to look into that question. And we have another one that says, compared with other satellite data such as Landsat with a spatial resolution of 30 meters, what are the benefits of PACE data? What's special about PACE data? So this person is referring to the fact that PACE has pretty coarse spatial resolution. And we have a few answers in the chat, and I'll add something as well. So for one thing, PACE is it's got the high global repeat. So we have global data every 1 to 2 days. When you have 30-meter data like Landsat, you get much less coverage. So maybe every 16 days you get a revisit. So they're actually really complementary for each other. You can see in the chat we have yep, that's what James has said. And also, of course, our spectral resolution, we have, there isn't any other satellite that gives global hyperspectral coverage of the globe every 1 to 2 days. So that's really where the power in PACE is. It also has some polarimeters. They give us phenomenal and advanced polarization data, which helps us look at the aerosols and clouds with a lot more, even more detail than we would have from OCI alone because they're using a different method. And I think I have gotten most of the questions. Can anyone, I don't know if anybody can see that I've missed one, or you feel free to retype it if I have missed one, but we are also at time. We can answer any other questions we may have missed as I mentioned, we do a question and answer transcript at the end. It's in our event archive with everything else. So I want to go ahead and thank Sky for giving us that fantastic presentation and tutorial, and also huge thank you to Dr. Charrington for presenting your cloud-based toolkit with PACE OCI land data. I hope a lot of folks put that to great use and are able to kind of get up and running with GEE, as several folks are eager to be doing. This is what we hear from our users. I want to remind you all to please fill out this survey. Help us plan our next meeting. As you can see, we can get our meetings, they can be pretty customized according to your requests. And we really want to help you guys get to work with the data. So with that, again, thank you everybody for coming. Thank you to the folks in our lab that are in the chat, also helping answer questions. Appreciate you guys being here. I hope all of you join us again at the next meeting, and I look forward to hearing from some of you guys on the presentations that you would like to give next time. With that, I will say thank you all for coming, and we will see you next time.